Hi, thanks for joining me. Today what I'm going to be doing is trying to find a value for 1 plus 2 plus 3 plus 4 plus so on off to infinity. Now you've probably seen the Numberphile video in which they evaluate this sum here and they prove that it equals minus 1 over 12. However, in today's video what I'm going to be doing is looking at the Riemann Zeta function and noticing what is this guy here. So zeta of s is the sum from n equals 1 to infinity of n to the minus s, and this is only defined when the real part of s is bigger than 1. However, if we plug in, or if we were to kind of plug in minus 1 into this guy here, we get the sum from n equals 1 to infinity of n to the 1, which is just 1 plus 2 plus 3 plus 4 plus so on. But of course this thing here is only defined for real part of s bigger than 1. So what we kind of want to do is find a function which is still nice and differentiable and continuous and whatnot, but it agrees with this zeta function on the real part of s bigger than 1, but it's defined on minus 1. So then we can just plug in minus 1 and try and find a value for this guy here. So that's what we're going to be doing in today's video. Let's get stuck in. Okay, so what I'd like to do now is introduce Abel's partial summation lemma, or sometimes just referred to as partial summation. So it's a lemma to do with complex numbers and sequences and series and integrals and combining all of them together. I'm not going to be proving it in today's video, but it's actually kind of a straightforward proof. You kind of follow your nose. So if you want to, do have a go at proving it yourself, and if you get stuck, just go ahead and look up the proof yourself. Anyway, this is a statement of the lemma. We have a sequence of complex numbers an, and we have a function f from the reals to the reals, which is continuously differentiable on some interval x, y. So x and y here are just real numbers. Okay, and we're going to define capital A of t to be equal to the sum of an from n being less than or equal to t. And I guess one thing I should point out here is n is just going to be the positive integers. So what I mean here is we're starting from n equals 1, n equals 2, and so on up to the biggest integer less than or equal to t. Because t here doesn't necessarily have to be an integer, it could just be a real number. So if we had t equals 3.2, then capital A of 3.2 would simply be little a of 1 plus little a of 2 plus little a of 3. Okay, and now the statement of the lemma is this thing here. We have the sum of n ranging from x to y, so we're going from strictly bigger than x to up to and potentially including y. So if x and y were integers, then we'd have the sum starting from x plus 1 and then finishing at y of an f of n is going to be equal to this guy here. So capital A of y f of y minus capital A of x f of x minus the integral from x to y of capital A of t times the derivative of f of t dt. Now, as I said, I'm not going to prove this in today's video, but it's not too difficult to go ahead and look up. But what we want to do is use this lemma here to try and understand the Riemann Zeta function a bit more. So what we're going to do is just define, I guess, an to be equal to 1. So it's a very simple sequence of complex numbers where every term is just 1. Okay, then what is capital A of t? Okay, well it's just this thing here, the sum from n being less than or equal to t of an, which is just 1. But essentially what we're doing here is just adding 1 for every integer less than or equal to t, or every positive integer less than or equal to t. So this thing here is simply going to be equal to the floor of t, okay? Because we're only adding integers, or positive integers, which are less than or equal to t, and that's equal to the biggest integer less than or equal to t, which is precisely the definition of the floor function. But another way we can write the floor function is simply t minus the fractional part of t. Okay, so if you've not seen this notation before, the fractional part of t is simply the bit after the decimal point. So for example, the fractional part of 7.2 is simply 0.2, like so. Okay, so that's another way we can write the floor of t. So capital A of t is simply t minus the fractional part of t. And now if we define, say, f of, let's use z to be equal to z to the minus s, and let's say we have x is equal to 1 minus epsilon, and we'll see why I'm using epsilon in just a second, because we're going to take epsilon going to 0, so our lower limit of the integral can just be 1. And what we're going to do is say let y equal capital N, and what we're going to do is take n to infinity. Then have a look at what we have here. So the sum from n going from x to y, well, x is 1 minus epsilon, so it's just a bit short of 1. So the sum is going to be from 1, so n equals 1, to capital N, okay, of an times f of n, which is just 1 times z to the minus s, or 1 times n to the minus s, which is just n to the minus s. Ooh, this is starting to look like the Riemann Zeta function. This thing here is going to be equal to, well, capital A of y times f of y. So that is going to be the floor of n. So A of y is going to be A of n, which is going to be the floor of n, times f of n, which is going to be capital N to the minus s. So we got the floor of n times n to the minus s. Now remember, s here has real part bigger than 1. So that means that the f of n is going to tend to 0 faster than a of n is going to tend to infinity. Because essentially, the floor of n is pretty much the same thing as n when n is large. So we've got roughly n times n to the minus s, which is going to be n to the 1 minus s. And s is bigger than 1, so that in the exponent you've got, or s has real part bigger than 1, so you've got n to some number, and that number has a real part less than 0, and hence it's going to tend to 0 as n tends to infinity. So n to the 1 minus s is going to be some number less than 0. Taking n to infinity means that whole thing is going to tend to 0. So this guy here is going to tend to 0, because we're going to take capital N to infinity. So if I just take n to infinity now, so just put this infinity there, we can ignore this term. And now we've got minus a of x, f of x. Well, a of x is a of 1 minus epsilon. So we're summing all the little a_n's up to n equals 1 minus epsilon. But n starts from 1, remember. So that means that capital A of 1 minus epsilon is just going to be 0, because there are no terms in this summation here. So it's just going to be 0. So this guy here also vanishes, which is really nice, as we take, or for any epsilon bigger than 0, I guess. But we're going to be taking epsilon to 0 in just a second. So all we have now is just this last part here, the integral. We've got minus the integral from, well, x, which is 1 minus epsilon, but we're going to take epsilon to 0, so it's just going to be integral from 1 to y. And remember, y is n, but we've taken n to infinity, so the integral from 1 minus the integral from 1 to infinity of a of t, which remember is just this guy here, so t minus the fractional part of t multiplied by f prime of t dt. But f is this guy here, so z to the minus s. If we differentiate that, we're going to get minus s times t to the minus s minus 1 dt. So I can bring this minus s out of the integral, because it's, the integral is only dependent on t. And this minus sign will cancel nicely with the minus sign we've got here. So we've got s times the integral from 1 to infinity of t minus the fractional part of t times t to the minus s minus 1 dt, like so. So it's gotten a bit messy, a little bit cramped down the bottom, but essentially we've got this thing here on the left hand side, which is precisely the zeta function. So zeta of s is equal to this thing here, s times 1, the integral from 1 to infinity of t minus the fractional part of t times t to the minus s minus 1 dt. So this might seem like it's just a bunch of nonsense. Why on earth would we bother writing this in nice form here into this weird looking integral? Well, it's going to look weirder in just a second. But what we're essentially trying to do is extend the domain of definition of zeta. Because remember, zeta is only defined for real s bigger than 1, and we want to eventually evaluate zeta of s at s equals minus 1. But to do that, we've kind of got to shift across the, or extend the domain in which we can define that, and that's exactly what we're going to do by playing about with this integral. Anyway, let me clean up the whiteboard and we'll continue. Okay, so we've just shown that zeta of s we can write in this form here, s times the integral from 1 to infinity of t minus the fractional part of t divided by t to the s plus 1 dt. Now, what we want to do is perhaps work with this integral a little bit and see if we can push some more out of it. So what we're going to do is use the fact that we've got t minus the fractional part of t and split this into two integrals first. So this is s times the integral from 1 to infinity of 1 over t to the s dt minus the integral from, or s times the integral from 1 to infinity of the fractional part of t all over t to the s plus 1 dt. Now, I guess one thing I should point out is this integral here actually looks very difficult to try and get an explicit value for. So let's see if we can work with this one here, which looks a little bit nicer. 1 over t to the s, well, we can just find a nice antiderivative to that. It's going to be s times, well, remember this thing here, I'm going to write it as t to the minus s. So this is going to be equal to, remember, add 1 to the exponent and then divide by the new exponent. So it's going to be 1 over, or minus 1 sorry, not minus 1, just 1 over 1 minus s times t to the 1 minus s from infinity to 1. When I plug in infinity, this guy here, t to the 1 minus s, that thing there is going to go to 0, because remember s has real part bigger than 1, so this thing here will go to 0. And when I plug in t equals 1, this thing here vanishes, and I'm just left with 1 over 1 minus s. So I've got 0 minus 1 over 1 minus s, which is the same as just 1 over s minus 1. So all in all, this guy here is just 1 over s minus 1. So when I multiply it by s, I'm going to get s over s minus 1. And then, of course, this thing here, minus s times the integral from 1 to infinity of the fractional part of t, all divided by t to the s plus 1 dt, like so. So zeta of s is equal to this thing here, s over s minus 1, so something relatively nice, minus s times this weird looking integral here. Now, although this integral looks weird and difficult to compute, let's have a further look at it. The numerator of this fraction is just the fractional part of t. And remember that, depending on what t is, it's always just going to be some number between 0 and 1. So this thing here is bounded above by 1. So this thing here we can just think of as less than or equal to 1. And this, what we're dividing by is t to the s plus 1. So all of a sudden we see that this integral here, I guess, if we just look at this thing here for a second, this thing here is going to be less than or equal to the integral from 1 to infinity of 1 over t to the s plus 1 dt. But what's nice about this is this thing here converges for s being, or real part of s, being bigger than 0. Because if s is bigger than 0, then the thing on the bottom is s plus 1 is going to be bigger than 1. And kind of, think of the harmonic series, or p-series test I think it's called. This thing here will converge, okay? And you can just, use your standard integration techniques by finding the antiderivative of that to show that it does converge. So all of a sudden we've taken the zeta function and we found it as s divided by s minus 1 minus s times some integral, and this integral actually converges for real part of s bigger than 0, whereas before all we had was real part of s bigger than 1. So all of a sudden we've extended the domain of zeta. So we've now got zeta of s being defined for real part of s being bigger than 0, whereas before we only had real part of s bigger than 1. However, I guess one little small thing to point out is this s minus 1 lurking in the denominator here, because we have zeta of s being undefined at s equals 1, because of course we can't do division by 0, but that's fine. So now we've defined zeta of s, sorry, if I get rid of this, this is for real part of s being bigger than 0 and s not being equal to 1. Which is really nice. We've extended the domain of zeta. However, notice that minus 1 isn't quite in this range just yet, or in this domain just yet. We've still got to do a bit more work. So let me clean up the whiteboard and we'll continue. Okay, so we've just shown that zeta of s is s over s minus 1 minus s times the integral from 1 to infinity of the fractional part of t over t to the s plus 1 dt. And I've written down a simple observation here, and that is that the integral from 1 to infinity of 1 over t to the s plus 1 dt is just equal to 1 over s. And we're going to use this observation here by noticing that if I multiply both sides by s, like so, I get that s times the integral from 1 to infinity of 1 over t to the s plus 1 dt is just equal to 1. Okay, and I want to kind of mold this thing here using my observation. So this is going to be equal to s over s minus 1. I'm going to leave a gap there, minus s times the integral from 1 to infinity of the fractional part of t, and I'm going to put a minus a half here, all over t to the s plus 1 dt. Okay, so same thing as here, except now we've got a minus half in our kind of numerator here. So what have we done? Well, we've essentially added on a half times s times the integral from 1 to infinity of t to the s plus 1 dt, but from this thing here, that's just going to be equal to a half. So we've added on a half, so we've got to subtract off that half, which I'll do here. Okay, so zeta of s is s over s minus 1 minus a half minus s times the integral from 1 to infinity of the fractional part of t minus half all over t to the s plus 1 dt. So all it looks like I've done is I've taken something that's messy and made it even messier. But of course, there is a reason for this, and I'm going to show you in just a second. And it's actually really beautiful why we've chosen a half here, because I guess I could have chosen any number there, but it'll become apparent in just a second. We're going to look at this integral in a bit more detail, and we're going to use integration by parts. And now what we want to do is integrate our numerator and then differentiate our denominator. So we're going to be letting u equal to the fractional part of t minus a half. Oh, sorry. No, we're not. We're going to be letting u equal our denominator, or which I'm going to write as just t to the minus s minus 1. So that's going to give us that du is just equal to minus s minus 1 times t to the minus s minus 2 dt, like so. And then dv is going to be our numerator, which is going to be the fractional part of t minus a half dt. So that's going to give us that v is equal to the integral of this. So I'm just going to write it as the integral from 0 to t of the fractional part of u minus a half du. Okay, so zeta of s is equal to this thing here, and if we just look at this integral in particular, perhaps I'll call this integral here I for now. We now have that I is equal to u times v, so it's t to the minus s minus 1 times the integral from 0 to t of the fractional part of u minus a half du, and that's evaluated from 1 to infinity, minus the integral of v du. But minus times the minus s minus 1 here is just going to give us a plus s plus 1 times the integral from 1 to infinity of v. So we get this function here, which I'm just going to call g of t for now, just to avoid confusion. G of t, so v times du, so that's going to be t to the minus s minus 2 dt. So I, just this part here, so not zeta of s, but just this part here, is going to be equal to this thing here, plus s plus 1 times this integral here. So making this very messy. Let's see if we can clear it up a little bit. Well, when we plug in t equals infinity here, this guy here is nice and bounded. So this thing here is, and this thing here goes to 0. So we've got something bounded times something going to 0. This all in all is going to go to 0. When I plug in t equals 1, I've just got the integral from 0 to 1 of the fractional part of u minus a half du. Now, if we just think about this, the fractional part of u, because we're doing the integral from 0 to 1, the fractional part of u is just going to be equal to u. So we're just doing the integral from 0 to 1 of u minus a half du. But you can just go ahead and work that out, or perhaps just think about what that looks like. So if this is our u-axis, u minus a half is going to look something like that. So if that point is a half, that point there is 1. So when we do the integral, we're doing this thing plus this thing. They're going to cancel out, so all in all we're going to get 0. So what's quite nice is this whole thing here vanishes. So we just can get rid of this completely. So we get that I is just equal to s plus 1 times the integral from 1 to infinity of g of t times t to the minus s minus 2 dt, where g of t is this function here, the integral from 0 to t of the fractional part of u minus a half du. But of course, this integral here involves another integral kind of hidden within g of t, so we've got to do a bit more work to have a play with this. But notice, or I guess one thing I'm going to show, is that we can write g of t very nicely, and we'll show that it's bounded. Once we can show g of t is bounded, we've now got the integral of something bounded times t to the minus s minus 2. So all of a sudden, this thing here is defined for a real part of s being bigger than minus 1, so strictly bigger than minus 1. Again, by the p-series test, because if real part of s is bigger than minus 1, then t to the minus s minus 2, if you think about this as g of t, or divided by t to the s plus 2, if s is bigger than minus 1, then s plus 2 is going to be bigger than 1, so by the p-series test, this thing here will converge, which is nice. So then we'll have defined it for real part of s being bigger than minus 1. So remember, we started with real part of s just bigger than 1, and now we've done kind of two different tricks twice, and resulted in s being bigger than minus 1, but that's not enough yet, because remember, we want to evaluate it at minus 1, but bigger than minus 1 is not good enough, so we need to do one more step. Anyway, let me kind of try and clarify what we mean here, but let me clean up the whiteboard first. Okay, so zeta of s is s over s minus 1 minus a half minus s times s plus 1 times integral from 1 to infinity of g of t over t to the s plus 2 dt, where g of t is this guy here, the integral from 0 to t of the fractional part of u minus a half du. But as I said, we want to have a look at this thing here, and remember, this choice of a half seemed kind of arbitrary before, but now I'm going to show you why it's actually a really smart choice, because we want to evaluate this integral here, or at least simplify it a little. Now imagine t is a really big number, say 8 you know, 8 is a very big number, so say t is like 8.2 or something. So let's have a look at this function here. Okay, so we've got, this is our u-axis, and this will be the fractional part of u minus a half. So as we had before, from between 0 and 1, it's going to look something like this. Okay, and then so the integral from 0 to 1 will just be 0, because this will cancel with this area here. But then if we have a look between 1 and 2, if this thing here is 3/2, the graph is going to look the exact same. Okay, because the fractional part of 1 plus, say, 1.01, that's just going to be the fractional part of 0.1, so 0.1. Then of course minus a half is going to give us what? Minus 0.4. So we're going to again start back down here and then go all the way up to just before 2. We're going to have the fractional part of just before 2, which is going to be just before 1 minus a half. So this thing here is going to go up to a half. And again, this area here is going to cancel with this area here, and so on. And you can see that this pattern is going to continue all the way up to just before t, so the integer just before t. So in fact, this thing here is the exact same as if we do this integral here. So we just start from the biggest integer before t and then go all the way up to t. Okay, because we know that everything before the floor function of t is going to have this property here, where if you just look at the integral integer by integer, it's going to evaluate out to 0. So g of t now is just this guy here. But in fact, we can go one step further, and if we have a look at what this thing here is, so if I get rid of this, and then just say zoom in, say that there is the floor of t, and let's say that's t, and that's going to be the floor of t plus 1, okay, like so. Well, what is this thing here going to look like? Well, it's just going to look like, well, this, say, okay, and this thing here would be the floor of t plus a half, so this would carry on like that in theory, but we're only considering this guy there. So it's just that little strip there. But notice that that little strip there is the exact same if we were to translate it back here and just do that thing there. Going from 0 now to this thing here would just be the fractional part of t. Okay, because it's very clear to see that the length of that interval there is just t minus the floor of t, which is precisely the fractional part of t. So in fact, we can change our limits here. Instead of the floor of t to t, we can just go 0 to the fractional part of t, of this guy here. Okay, so zeta of s, not zeta of s, g of t is just this thing here. But now what's really nice is, remember, the fractional part of t is always going to be less than 1. It's going to be at most 1. And so that means that in this interval here, the fractional part of u is just going to be precisely equal to u. So in fact, we can get rid of the fractional part here. And now we've got an integral which we can actually go ahead and just compute. This thing here is going to be equal to a half u squared minus a half u. And that's between the fractional part of t and 0. So that's just going to be a half times the fractional part of t squared minus the fractional part of t, like so. So g of t is equal to this thing here, and this is kind of in explicit form. And the reason for that, or the reason we could do this, is because of this half here, which meant that we got this really nice cancelling out when we tried to compute the integral. Okay, so g of t is equal to a half times the fractional part of t squared minus the fractional part of t. And one thing I'm going to point out is this thing here is at most 1, this thing here is at most 1. So all in all, this thing here is going to be at most 2. So g of t here is going to be at most, or in fact, that's going to be at most 1. And I guess I'm doing minus the fractional part of t, so that thing there is going to be minus the fractional part of t is going to be some number between 0 and minus 1. So that's going to be at most 0, that's going to be at most 1. So all in all, this is going to be at most 1. And then I've got a half there, so g of t is going to be less than or equal to half. And in fact, we can bound that a bit better if we wanted to. But g of t is nice and bounded. So that means, like I said before, we can now note that this thing here is an integral which is defined for real part of s strictly bigger than minus 1. So we've extended the definition of zeta of s again. Remember, s equals 1 is kind of like a little touchy spot. We're going to ignore that for now. It's not, zeta of s doesn't converge at s equals 1. But we don't need to worry about s equals 1. We're only interested in s equals minus 1. And now all of a sudden we've defined zeta of s for s, real part of s, being bigger than minus 1. But as I said, that's not enough. We've got to do one further step. But let me clear up the whiteboard and we'll continue. Okay, so we just showed that zeta of s is equal to s over s minus 1 minus a half plus s times s plus 1 over 2 times the integral from 1 to infinity of the fractional part of t minus the fractional part of t squared all over t to the s plus 2 dt. Now, I've written 3 dots here and written another ugly looking line, and the reason I've written 3 dots here is just to keep the video from becoming ridiculously long, but essentially use some really similar techniques, and you can show that zeta of s actually equals this guy here, 1 over s minus 1 plus a half plus s over 12 minus s times s plus 1 times s plus 2 times the integral from 1 to infinity of the fractional part of t minus the 3 times the fractional part of t squared plus 2 times the fractional part of t cubed all over t to the s plus 3 dt. And going from this line to this line, all you really focus on is this integral here, and again do integration by parts, but perhaps introduce a factor, like before we introduced the factor of a half into the numerator, so you've got to add on another factor like that. But if you want, I'll leave the details of that to you. It'll be a fun little exercise. But for now, we're just going to use this thing here, and as we see here, the numerator, everything here is between 0 and 1, so this numerator is nice and bounded, so we've just got something bounded divided by t to the s plus 3, so that thing there is certainly going to be integrable. The integral, sorry, is going to converge for real part of s bigger than minus 2. Okay, so zeta of s, this integral here is defined for real part of s bigger than minus 2. This is defined for all s, this is defined for all s, this is defined for all s. This thing here is defined for all s except s equals 1. So all in all, we've defined zeta of s for any complex number s with real part bigger than minus 2 and s cannot be equal to 1. But thankfully, minus 1 falls in that kind of range of numbers, so we can just go ahead and plug in minus 1 into all of this. So zeta of minus 1, well, when we plug it into here, we're going to get 1 over minus 1, so that's going to be 1 over minus 2, so that's minus a half. Well, plus a half, that's nice. Minus 1 over 12, oh, that's interesting. And then we've got minus, well, s times s plus 2, but the thing we're interested in here is this s plus 1 here. When we plug in s equals minus 1, this is going to kill this whole term here, which is really nice. So s equals minus 1 makes this whole thing vanish. So zeta of minus 1 is just this guy here, minus a half plus a half minus a 12th. And, well, you can do the maths here. This just equals minus 1 over 12, the grand finale. And would you believe it, it is the exact same number that Numberphile got in their video, because minus 1 over 12 is actually what you would get rigorously, and their proof in their video wasn't very rigorous. It was just rearranging, illegally rearranging some infinite series. But this is kind of a lot more rigorous. Of course, this does not mean 1 plus 2 plus 3 plus 4 plus so on equals minus 1 over 12, unfortunately, but it does mean that the Riemann Zeta function, when you extend it, or what's known as analytic continuation, you're going to get a nice function where you plug in minus 1, you get minus 1 over 12. Anyway, I hope this has all made sense, and to stop this video being really long, I'll stop it here. Thank you for watching. I'll catch you in the next one. Have a great day.